Okay, this is a joint work with Gianluca Guadagni, Carlo Lancia, and Benedetto Scopola. The plan of talk is about arrival process, a queuing system, the functional equation of the system, and the asymptotic behavior of the stationary distribution of the system. Initial arrival process. Okay. In classical queuing theory, it's folklore to assume that inter-arrival times are represented by the IED sequence of random variables. I.e., the queuing system is where arrivals occur according to a renewal process, for example, Poisson process. And now let us consider the following stochastic point process that is represented by Ti. It's equal I over lambda plus XI, where XI are IED random variables with variance sigma square and probability density function that is Riemann integral. And lambda is real strictly positive that represents the rate of arrivals. The first thing to do is to compare this process that I call a star process. One can prove that the star process weakly converges to the Poisson-Pont process with intensity lambda when s sigma tend to infinity, and its version of its inversion still converge to the Poisson-Pont process with intensity rho lambda, where rho is the probability to retain a point in the point process. And one can prove still process has negative autocorrelation. It means that the process is it's not a renewed process, and the this process is different from Poisson process. Our goal is to study a single server queue with a simple single server queue with unit determinate series time. Units of the arrivals are described by the star process, i.e. the queuing system GD1 in terms of Kendall notation. This model is motivated by the description of the system where scheduled arrivals are subject of random variation, like public and private transportation system, aircraft, trains, boats, or vessel marine traffics, etc. The appearance of the stochastic point process can be traced back by works of Wilson work, 59. Wilson named it a late process and obtained results for a special case where the customers can never be delayed more than 2 unit times. Same problem was investigated also by Kendall, considered father of the queuing theory, where he remarked the great importance of such systems. Now, let us consider the simple case. Okay, I want to study silver queuing system defined in the following way. There is a customer arrived to the system at time Ti, Ti, I
this XCI. Now a lambda is equal 1, and XCI are ID exponential random variable with parameter beta. After Kendall, we name this arrival process exponentially delayed arrivals, or EDA. And the service times of each customer is constant of size 1. Remember that the arrivals do not form a new process, since the arrivals times are correlated. And we decide to delete each customer independently with probability 1 minus rho, i.e. independent thing of the arrival process. Let us define the length of queue at time t by xt, which is governed by this stochastic recurrence, where here mt is the number of arrivals in the interval, unit interval, t plus t, and the delta is simply delta Kronecker delta. Okay. Clearly, xt is not Markov. Remember, since the MT depends in general on the previous history of the system. So to study this process, it is difficult, since in this case the standard theory or classical queuing theory function. Let us introduce the new process that we call this late process. LT is the number of customers that have not arrived yet at time t. That is the cardinality of this set. And defined P is equal integral of density function of exponential random variable. This is 1 minus Q, where Q is exponential of minus beta. Okay, now we use the memoryless property of the exponential delays, XCI, and it is easy to see that the random variable MT is, given the value of LT is binomially distributed with parameters LT and P. Then we have this obvious consequence. In order to study our system, we consider a couple XT-LT. And given the relation to or memoryless property of XCI, we can see that this couple is Markov chain on the non-negative quarter plane. And one can prove this lemma that this bivariate Markov chain is ergodic only if Q and rho are less than 1. And the lemma guarantees both the existence and the uniqueness of the stationary distribution, that is PNL, is defined in this way. Now, in
order to obtain PNL, okay, we define the generating function, bivariate generating function, and we obtained this result. The generating function of PZ satisfies this functional equation. This functional equation sadly do not admit simple or immediate solution. Is different from the functional equation typically studied in the literature. It's a famous book by Fayol, Yesnagorski, and Malishev, and it is special in this respect. So we don't have still now we don't have a solution, but we can see in particular case when Q is equal to 0, it's easy to see that PZ solution is given by that is generating function of the DD1Q system with bulking. And in case Z equal 1, the solution of functional equation is given by the infinite product. This infinite product has interesting combinatorial interpretation. It's related with is so-called infinite cube Pochhammer symbol. This is related with the well-known Euler function. Now we want to study the behavior, asymptotic behavior of the PNL, the stationary distribution of the system. Initially, in order to do that, we can invert the generating function P1 epsilon in order to obtain the PL, that is the distribution of the late customers. Okay, this is given by this formula 8, and using from 8, we can obtain that this upper bound of PL on the leading term is rho power L Q power L plus 1 choose 2, and term minus essentially is the Euler function. This is constant. And now let us consider the auxiliary process alpha t. This is xt plus LT. We can interpret this alpha t as a diagonal in the quarter plane, where the point xt, LT, and so on. And under equilibrium condition, the probability of finding the system on the alpha diagonal is clearly given by this relation P alpha. It's written in terms of PNL, the joint distribution. Now let's define a generating function of the pi alpha. Sorry, there is a mistake. Alpha is greater than 0. this case, we have that QZ is well of PZZ, and still in this case we are not able to solve this functional system, apparently simple. But we can use this functional equation to write the measure P alpha in terms of P0 0 alpha, and finally we obtain minor result. This is the equilibrium distribution P and L. In the case super exponentially fast as N and L tend to infinity. And this theorem gives the possibility to compute approximately the joint stationary distribution Pn numerically. And that's all. Thank you very much.